Okay, so now we understand where Gaussian elimination is going to let us down. Now let's think what we're going to do about it. So let's look at iterative methods. Now I'm just going to show you the overall idea behind what we're doing before we jump in with a specific example. So you always start off by just choosing some values for what you think the solutions of your linear system of equations are going to be. Now this might be based on something that you already know. It might be based on an educated guess. For example, you think that the value should be around this, or they may be genuinely just a pure guess. You just choose some random numbers to go in there. Nonetheless, you need to choose some initial values to start off with. You then use those initial values to do some kind of computation. Now, this computation is based on the equations which you have got to try and solve, right? So they don't just get plucked out of thin air. You use the equations that you're trying to solve to form some computational equations. And then by solving these computational equations using your initial values, you end up with some new values. Now, it doesn't stop here, because these new values probably, at this point, are going to be pretty terrible. So what you're going to do instead is just take these new values and plug them back into your computation equations to get even more accurate values. And basically you just keep doing this process. You keep iterating over this idea until you end up with values that you're pretty happy with. Now, just a word of warning. With this particular method, with iterative methods, you're probably never going to get an exact solution. You're probably going to get as close as you want, but basically you need to decide what accuracy level you're going to be happy with. You're never going to probably get it exactly, but you need to be happy. For example, I want my solutions to 3 decimal places, so you basically just keep doing this process of plugging things back into equations, choosing what values you get out, then plugging them straight back in again. You keep doing this until you get to a degree of accuracy that you are happy with, okay? But the idea is you're probably never going to get exact equations. That's just a word of warning. So the first example that we're going to look at is something called Jacobi's method. Now, just to be aware, we've just said that Gaussian elimination kind of breaks down when we have huge systems of equations. But just to illustrate the method, I'm just going to stick with my system of 3 equations with 3 unknowns, just until we get the idea. So let's suppose I want to solve this system of 3 equations with 3 unknowns. I can't use Gaussian elimination. Perhaps there's some reasons, I can't store it, or it's going to take too long. So in which case, I need to figure out another way of doing it. Well, okay. If I just gave you these 3 equations to solve, and if you didn't know about Gaussian elimination, what you would probably try and do is say, well, look, here's my first equation. I can rewrite my first equation in terms of my first unknown, namely, x1 is going to be equal to, well, okay, I'm going to take my 21, I'm going to take away all of the unknowns which aren't x1, so in other words, the 4x2 and the x3 term, so in other words, that's all on the right-hand side, and of course, I also need to divide by 10. So in other words, if I just rearrange this first equation in terms of x1, this is what I get, okay? And if I do a similar kind of thing for x2, so x2 is going to be, well, let's see, 51 minus 2x1 minus 3x3, all divided by the coefficient of x2, which is 20, and similar kind of thing for x3, so in other words, 37, take away x1, take away 3x2, all divided by 10. Okay, so in other words, if I was going to rearrange this system of equations, so equation 1, equation 2, and equation 3, in terms of the 3 unknowns, so in terms of x1, x2, and x3, then this is the system of equations which I'm going to form, okay? Now I can basically use this to form my iterative methods. So basically I'm going to start off with my initial values. These are kind of my guesses, if you like. Now, at the moment, I have no idea what my initial value should be. I have no idea what my solutions should be. So I'm just going to choose them all to be 0. So I'm going to choose x1, x2, and x3. And I'm going to just choose them all as 0. So 0, 0, and 0. Now what I'm going to do is basically plug in my values of x1, x2, and x3 into the right-hand side of my equations up here in order to get my new values of x1, x2, and x3. So let me demonstrate, okay? If I plug in x1 is equal to 0 into my top equation, I basically get 21 minus 4 times 0 minus 0 all divided by 10, which comes out as 2.1. So that there is going to become my new value for x1. If I do exactly the same thing with x2, now remember, this is my new value of x1, so I'm still going to be using my old value of x1 when I come to plug it in for my second equation. So in other words, if I plug it in, I get 51 minus 2 times my old value of x1 was 0. So I'm going to get 2 times 0 minus 3 times 0, all divided by 20. Okay, so if I do that, I find that this comes out as 2.55. So that's going to be my new value for x2. And if I do the same thing for x3, so again, plugging in my old values of x1 and x2 on the right-hand side, then I get 37 minus 0 minus 3 times 0, all divided by 10. Well, okay, that comes out as 3.7. So in other words, after the first step of Jacobi's method, I find that my new values of x1, x2 and x3 are 2.1, 2.55 and 3.7. So in other words, my new values after my first one is going to become 2.1, 2.55 and 3.7. Now clearly, this is just after one step. If I want to increase the accuracy, what should I do? Well, I should do this step again. In other words, I should go back and now plug in my x2 and x3s and x1s into the right-hand side of my equations, but now using my 2.1, 2.55 and 3.7. So just to illustrate that, basically I'm going to change this 0 to 2.55. I'm going to change x3 now to 3.7, and I'm going to divide it by 10. And if I do that, I find it comes out as 0.71. So that's now my new value of x1. Okay, if I go back and if I plug in my other values, so okay, I've got x1 here, which is now 2.1, and I've got x3 here, which is 3.7, I find that my new value of x2 comes out as 1.785. That's my new value of x2. And again, if I go back and if I plug in x1 and x2 into my third equation, okay, so x1 was 2.1, and x2 was 2.55. So when I plug that in, I basically find out it comes out as 2.725. Okay, so that's my new value of x3, so 2.725. Okay, and in fact, I can keep going like this. So I can now plug these equations into my equations above. And I find if I do that, x1 becomes 1.1135. My x2 becomes 2.07025. My x3 becomes 3.0935. And if I do it again, if I want to, I can do it as many times as I like. I'm going to do it one more. So 0.96255 is my new value for x1. 1.974625 is my new value for x2. And 2.967575. So basically, the idea is the more I do this particular method, I'm converging towards some particular values. So it looks as if x1 is going to be about 1, x2 is going to be about 2, and x3 is going to be about 3. Now I know, because I set this system of equations up at the very beginning, that I know that x1, x2 should be 1, 2, and 3. But the important thing is, look, you notice it's not exactly 1, 2, and 3. It's pretty darn close, but it's not exact. And the reason being is because I'm using this idea of iterative methods. So the idea is, the more I do this kind of step, the more I do this kind of idea of taking my values, which I get out and plug them straight back into my equations, the more I do that, the closer I should get towards my actual solutions. So okay, now we've got the idea, okay, let's actually try and generalize it. So I'm just going to start off with 3 unknowns, get the idea across, because it's really important to be able to generalize it in order to then code it up into a computer. So let's suppose I have the coefficients, okay, and you can see that the way I've written the coefficients kind of correspond to the row and the column of the coefficient matrix. And I've got x1, x2 and x3, and then b1, b2 and b3 are my known values on the right hand side. So, okay, let's take my first equation, my top equation, and let's rearrange it for x1. So I can basically say that x1 is going to be equal to, okay, so when I rewrite this, it's going to be equal to b1 minus a12 times x2 minus a13 for x3. And of course I'm going to have to divide that by the coefficient of x1, which of course is a11. And if I do exactly the same thing for the other 2 equations, then I get this, like so. So basically I've just rewritten all the top equations in terms of x1, x2 and x3. Now there's a couple of things I need to be aware of here. Number 1, the x1 and x2 and x3 on the left hand side basically correspond to my new values of either x1, x2 and x3. Okay. all of the x1s, x2s and x3s on the right hand side correspond to my old values. In other words, the values which I get when I stick them in. Okay, so either my initial guesses or my older values. Okay, so in other words, if I let that all of these are going to be the values at the kth step, so I just put them in a little bracket up here. So these are all the values that I'm going to have at the kth step. Then the numbers on the right hand side are going to be the values which I'm going to have at the k plus 1th step. In other words, at the next step along. Okay. Now that's just really useful because what I'm going to do now is basically think about what it's going to look like in general. Okay. So in other words, in order to get this done in general, can you see that I can basically write that x1 at the kth step, sorry, the k plus 1th step rather, will be equal to whatever the first equation is, so it'll be b1, take away the sum of, okay, so I need to basically take away the sum of the coefficients in that particular row times by the unknown. So I'll take the sum from j equals 2 in this case, right the way to how many unknowns I've got, times by a, well it's the first row, so it'd be a1, but I'm going to basically change the column because I'm going to be working way across the column, times by xj, so that's going to be my unknown, all divided by my a11 in that case. And if I just show you for the next one, so it'll be x2 at the k plus 1th step. Of course, this is xj at the kth step. X2 at the k plus 1th step is going to be b2. Take away the sum. Well, okay, I will start it at 1, but I can't have j is equal to 2 because obviously that's the equation that I'm trying to solve it for. Okay, right the way through to n of a2j times by xj at the kth step. Now, all divided by, of course, a22. And of course, you can carry on like this to find the nth general term. But hopefully that's enough to give you an idea of how to generalize this, particularly if you're trying to code it up or something like that. Okay. Now let's think about what the limitations of Jacobi's method actually is. And actually the reason why I've written it out like this, the reason why I've thought about how we're going to sort of generalize this, is because it's really obvious what we need to be careful of. And the thing obviously we need to be careful of is that the A11, the A22, the A33, the A44, the A whatever, as long as it's an element on the diagonal, then that can never be 0, because clearly the way that I'm generalizing this, the way that I'm forming Jacobi's method, is by dividing by the diagonal element, because that's going to be the element which I'm trying to, the coefficient of the element which I'm trying to solve. So in other words, one of the limitations which I need to make sure of is that the diagonal is never 0. So limitations. So one of the first ones is that the elements on the diagonal are non-zero, because clearly I can't divide by 0. Now, you might be saying, well, what if I do have a diagonal element being 0? Well, that's okay, because you might be able to rectify that by swapping rows over, just like we did with Gauss elimination. When we formed that multiplier, we basically took the pivot divided by, or the element which we're trying to delete divided by the pivotal element. Now, clearly, if the pivot was 0, then we could just swap the rows over and it kind of rectified itself out most of the time. So same kind of thing here. If we do have a diagonal element being 0, try and just swap the elements over. So that's one important point. Okay. The other thing we need to be careful of as well is whether it's going to actually converge. Now, what do I mean by that? Well, you notice that what I started with, so my starting sort of guess, was literally just a guess. Okay, my starting values was literally just a guess. So in this case, I started with 0, 0, and 0. That was my initial values that I started with. Now, it may be the case that my initial guess doesn't actually mean it converges. In other words, it gets further away from the true solution. So what I need to make sure, okay, there is a condition which I can check to make sure it does converge, and it's basically to make sure that the elements on the diagonal are always going to be bigger than the sum of all of the other coefficients. So you remember the diagonal elements are the coefficients of the variable that we're trying to solve, or the unknown that we're trying to solve at each step. Okay, so in other words, if I take the coefficient there, as long as it is big enough, in other words, it's bigger than all of the other values added together on that particular row, then I'm pretty sure that it's going to converge. Okay, now just to be clear here, because it may be that some of the other diagonal elements or some of the other row elements are negatives, that's perfectly possible. I'm just going to use absolute values just to make sure that we're not doing any cancellations. Okay, So in other words, I'm just going to make sure that these are all absolute values. So in actual fact, this is kind of sloppy notation. So let me write it out properly. So I'm going to write that the diagonal elements, which is AII, so in other words, same row, same column, absolute value has got to be bigger than the sum of all of the other elements on the row. So in other words, J is equal to 1, not including the ith element, of course. Okay, so not J is equal to I, right the way through to n of that particular element there. So it's going to be I, J. Okay. So basically, as long as the diagonal is dominant, in other words, it's bigger than all of the other coefficients on that particular row, we're pretty sure it's going to converge. If it's not, it's kind of touch and go whether it is actually going to. So I guess the final thing to do then, before we finish with Jacobi's method, is to compare what its advantages and limitations are with respect to Gaussian elimination. Well, okay, the first thing which I don't like about Jacobi's method is that there could be potentially infinite steps. Okay, sorry, infinite steps. Okay, so unlike Gaussian elimination, where we know that with naive Gaussian elimination there's going to be n-1 steps to forward elimination, so there's a finite number of steps, with Jacobi's method we know that we're going to probably, or we could have, an infinite number of steps. Okay, but that's not to say that Jacobi's method is bad, because actually Jacobi's method does have some advantages, such as, for example, we never change the coefficient matrix A. Now again, we've discussed that with the cost of Gaussian elimination, the way that we store sparse matrices is generally the case that we just store the non-zero elements and their positions. Now because in Jacobi's method we're never actually changing that matrix, that's fine. We never need to think about how we're storing things, we never need to update the storage at all. Okay, so we don't need to worry about changing A with Jacobi's method. Okay. We also need to be aware that Jacobi's method, we can never divide by 0. Now I've said that the way which we form those equations, you know, the way which dividing by the numbers on the diagonal of our coefficient matrix, as long as they're not 0, we might be able to swap them over, that's okay. However, there may be a situation where we simply cannot swap that particular diagonal. For example, we just simply don't have that particular unknown. Okay, any coefficients in that unknown, we can't swap them over. Or if we do swap them over, it prevents us from solving some of the other equations. So as a result, because we've got this issue that we can't divide by 0, Jacobi's method may not work. Okay, so it may break down. Okay. But another advantage, which is actually just like Gaussian elimination, so I wouldn't call this an advantage or elimination, an advantage or disadvantage. What I would say is that this is kind of equal to Gaussian elimination, is that we are allowed to swap rows over. Just like we were with Gaussian elimination, we can swap rows without changing the values of our unknowns. Okay, so if you're just thinking about comparing Jacobi's to Gaussian elimination, you've got to be aware Jacobi's method may include an infinite number of steps. In other words, you need to choose what degree of accuracy you want, okay? Because there may be an infinite number of steps that you can carry this on for. One of the advantages of Jacobi's method to Gaussian elimination is that we never have to change that coefficient matrix. In other words, we don't have to worry about re-updating the way in which we're storing our coefficient matrix. But we do have to be aware that there are some situations where Jacobi's method may break. For example, like I said, we might be dividing by 0, so the diagonal elements, we may have 0, and we simply can't do any swapping rows to rectify that. We may also have the situation, of course, that it may not converge. In other words, it might diverge. For example, I said above that that it will converge in general if the diagonal is dominant. In other words, if the element on the diagonal is more than all of the other elements on that particular row added together. Of course, considering absolute values, because we don't want to have any cancellations. Okay, but it may be the case that that's simply not true, in which case we may end up with a situation which may diverge. Okay. The other advantage, of course, which is not really an advantage compared to Gaussian elimination, it's kind of equal to it, is that we are allowed to swap rows. Okay, so hopefully that makes it a little bit clearer about what Jacobi's method is all about.